Two blocks connected with a pulley. Consider the system shown in figure. The rope and the pulley have negligible mass, and the pulley is frictionless. Initially, the 6 kilogram block, which I have labeled 1 here, is moving downward, and the 8 kilogram block, which is the second block here, is moving to the right with a speed of 0.9 meters per second. The blocks come to rest after moving 2 meters. So this moves down 2 meters, this moves to the right 2 meters. Use the work energy theorem to calculate the coefficient of kinetic friction between the 8 kilogram block and the tabletop. So there is friction between the second block and the tabletop. We are to determine the coefficient of kinetic friction. So let's start with drawing a free body diagram for the 6 kilogram block. I'm going to solve this problem in two different ways. So for the 6 kilogram block, which I have labeled block 1 here, there are two forces acting on it. There is the weight and there is the tension, which is pulling it up. So this is modeled as a particle feeling two forces, mg and 1g pointing down, and the tension T pointing up, and we have the y-axis, the vertical axis. Now this has an initial kinetic energy 1/2 m1 v1 initial square, and this is a 6 kilogram block, so this is 1/2 times 6 times, remember they were moving together with a speed of 0.9 meters per second initially, so this has a speed of 0.9, so 0.9 square gives me an initial kinetic energy of 2.43 joules. What is the final kinetic energy of this block? It is 0 because it's going to stop. So how much is the change in the kinetic energy of this block? Well, it's 0 minus 2.43, so it's minus 2.43 joules. What is the initial potential energy of the first block? Well, it is m1g h1 initial, 6 kilogram block, gravitational acceleration 9.8 meters per second square, and it's moving downwards 2 meters, so it has an initial height of 2 meters. This gives me 117.6 joules. Final potential energy is 0 joules. The change in the potential energy is minus 117.6 joules. Okay. Now I'm going to move on to the free body diagram of the 8 kilogram block. So that's the second block I have labeled here. Free body diagram of the 8 kilogram block. So we have the weight pointing down, m2g. There's a normal force from the horizontal table, normal force acting on this one. The tension on the rope is pulling it to the right. And then we have kinetic friction opposing the motion pointing to the left. So these are the four forces: the weight, the normal force, the tension on the rope, and the kinetic friction. Now, what is the initial kinetic energy of the second block? It is 1/2 m2 v2 initial square. This is an 8 kilogram block, so it is 1/2 8 times 0.9 square, that gives us 3.24 joules. Eventually it's going to stop, so final kinetic energy is 0 joules, and the change in the kinetic energy is minus 3.24 joules. The potential energy of this block is not changing because it's always moving on this horizontal table. The net force on the y-axis is 0 because there's no motion on the vertical axis, so the normal force is balancing the weight m2g. Therefore, the force of friction, kinetic friction, is coefficient of kinetic friction times the weight of the block, mu k m2g. Okay. So if I concentrate on the 6 kilogram block, for the 6 kilogram block, the net force on the y-axis is basically tension minus m1g in the plus j hat direction, and the work done by the net force is equal to the net force tension minus m1g pointing in j hat direction dot product with delta y in j hat direction. So this is tension minus 6 kilogram times 9.8 meters per second square. The delta y is, final y is 0, initial y is 2 meters, 0 minus 2, and this must be equal to the change in kinetic energy of the first block. Why? Because we have work kinetic energy theorem. The work done by a net force is equal to the change in the kinetic energy of the system. So if I plug in the numbers here, this is going to be 2 times 6 times 9.8, 117.6 minus 2t. That's equal to the change in kinetic energy minus 2.43 joules, if you remember, for this one. And this gives me 2t equals 117.6 plus 2.43, and therefore I find that the tension on the string is 60.015 newtons. And if I concentrate on the 8 kilogram block free body diagram, the net force on the x-axis for this one is basically the tension minus kinetic friction. The work done by the net force is tension minus mu k m2g I hat dotted with displacement in the I hat direction. This must be equal to also the change in kinetic energy of this block. Once again, I'm using work kinetic energy theorem, and when we plug in the numbers, this is the tension was 60.015, mass is 8 kilograms, 9.8 mu k times 2 y2, because we have 2 meters in I hat direction. The change in kinetic energy of this block was minus 3.24 joules. So this is minus 3.24 joules. So this gives me 120.03 minus 156.8 mu k is equal to minus 3.24, and I find mu k as 120.03 plus 3.24 divided by 156.8, and that gives me 0.7864 coefficient of kinetic friction. So this is one way to do it. There is an easier way, so let me talk about that. Alternatively, I could concentrate on the system A plus B. Okay. So the change in the mechanical energy of the system A plus B is delta K1 plus delta K2 plus delta U1 plus delta U2. So delta K1 was minus 2.43 joules, delta K2 was minus 3.24 joules, delta U1 was minus 117.6 joules. The second one doesn't have any change in the potential energy. This gives a total of minus 123.27 joules. And because we have friction in the system, this must be equal to the work done by the external force on the system, which is consuming energy. So this is basically work done by friction minus mu k m2g delta x. So this becomes minus mu k 8 times 9.8 times 2 minus 156.8 mu k. So mu k, coefficient of kinetic friction, becomes 123.27 divided by 156.8, which gives us 0.786, the same answer we have found before. So basically what we have done is that observing A plus B is not an isolated system. The total mechanical energy of this system decreases due to friction. Okay, so if we go back, we have two blocks, block 1 6 kilograms, block 2 8 kilograms. They have an initial speed 0.9 meters per second. The system is moving down. After moving 2 meters, the blocks come to rest. Why? Because there's friction on this table opposing this motion. So we are asked to find the coefficient of kinetic friction using work energy theorem. So first I concentrated on the 6 kilogram block free body diagram. Tension minus M1G is the net force acting on the y-axis. I calculated its initial kinetic energy, 1/2 M1 V1 initial square. Final is 0 because it comes to a stop, it comes to rest. The initial is M1GH, so we have 2 meters from the ground and then we fall 2 meters. Final is 0. So we can calculate delta K1 and delta U1. For the 8 kilogram block, we have the normal force, the weight, tension, and kinetic friction opposing the motion. And kinetic friction is mu k m2g because the normal force is balancing the weight. There's no motion on that axis. And the change in kinetic friction is basically found by taking 0 for the final kinetic energy. Initial kinetic energy is 3.24 joules due to the common speed 0.9 meters per second, and there is no change in the potential energy of this block. So concentrating on the 6 kilogram block, if we calculate the work done by the net force is T minus M1G in J hat direction, dot product with displacement in J hat direction. The displacement is actually in minus J hat direction, so we have 0 minus 2 here, delta Y is minus 2. So this gives us the change in kinetic energy due to the work kinetic energy theorem. Delta K1 was calculated before, so this gives us the tension. And if I concentrate on the 8 kilogram block, the net force acting to the right is tension minus kinetic friction, as you can see on this free body diagram. Work done by the net force, we have to take the dot product of the net force with delta x in I hat direction is equal to the change in kinetic energy, so this gives us the value of mu k. On the other hand, if I add up all the energy terms, all kinetic energies and potential energies, I find the mechanical energy of the system. There is a change in the mechanical energy of the system of minus 123.27 joules, and this is why this is due to the fact that we have friction in the system. It's not an isolated system. So the change in the mechanical energy of the system is work done by the external force minus mu k m2g delta x. So this also gives us the same value for the coefficient of kinetic friction. This is between the horizontal table and the 8 kilogram block. As you can see, the 6 kilogram block is not touching the table.